let's do an example of constant acceleration motion. Since it's a fairly common example that we have everyday experience with, we're going to use the acceleration of gravity as our example. So let's say here you are. You're tossing a ball up in the air. You toss it up with an initial velocity of 30 meters per second. Gravity is going to pull it down at about negative 10 meters per second squared. So we're rounding that up. And we're going to look and see what happens at different times. So at time t equals 0 seconds, 1 second, etc., etc. We're going to see how high we are from our starting point, what our velocity is, what our acceleration is, and what our average velocity is. So let's see if we can figure out what each of these values are at each of these different times. Well, we're going to start off by defining our origin, our y equals 0 height, to be just the height that the ball gets released at. And we'll say that the upward direction is positive. So as we go up, you will get a bigger positive number for your height. Okay, but we're starting off at a height of 0. We're starting off with a velocity of plus 30 meters per second. That was given. And we know the acceleration of gravity is going to be negative 10 meters per second squared. And that's a constant. So I can actually fill out this whole column. For every time, my acceleration is going to be negative 10 meters per second squared. It's always going to be that, until I hit the ground. Once you hit the ground, if you get stuck in the ground, then you're not accelerating anymore. Your acceleration will be 0. But as long as the ball is in the air, the acceleration is going to be negative 10 meters per second squared. All right, we know acceleration tells me how my velocity changes. And we know we're going down 10 meters per second every second. So that would mean that after 1 second, I've gone down from 30 meters per second to 20 meters per second. And after 2 seconds, I would have gone down another 10 meters per second. So that'll get me to 10. At 3 seconds, I've gone down another 10 meters per second. So that means I have a velocity of 0 meters per second. That's not a problem. Technically I'm not moving at that split instant. But we are accelerating. We are accelerating in the negative direction. So you will eventually start to come down. Coming down means you're not going to have a negative velocity. Again, we're just going down by 10 in the velocity. We'll go down by 10 once more. That will be negative 20 meters per second. So all we're doing to change the velocity is just going down by 10 meters per second. Because again, our acceleration is negative 10 meters per second every second. Next, I want to consider what my average velocity is. So this is how fast have I been moving on average from 0 to 2 seconds. All right, well, my average velocity to start off with, it's not much of an average because I only had 1 point. But on average, I've been moving 30 meters per second. Put this in meters per second. I'll write that there so I don't have to write out the units every time. Well, now, how fast have I been going on average after 1 second? Well, I started at 30, and I ended up at 20. I've gone down. What's the average of 30 and 20? Well, if I take the average of 30 and 20, taking the average is really just a matter of adding the 2 and then dividing by 2. Or to put that another way, it's just the midpoint between the two numbers. So the average velocity between 0 seconds and 1 second, or when we're traveling, the average velocity between 30 meters per second and 20 meters per second is just going to be 25 meters per second. So on average, that's how far we've gone, how fast we've gone. What's the average velocity when I go from 30 to 10 meters per second? Well, between 0 and 2 seconds, we've gone from 30 meters per second to 10 meters per second. What's the halfway point between 30 and 10? Well, that's 20 meters per second. So on average, our velocity is only 20 meters per second there. So for the first 2 seconds, we have been traveling an average of 20 meters per second. So initially I was moving at 30 meters per second. Between 0 and 1 second, on average I've been traveling 25 meters per second. So how far have I gone if I've traveled 1 second with an average speed of 25 meters per second? If I've gone 1 second at an average speed of 25 meters per second, it should be true that I have traveled 25 meters, positive 25 meters. So you've gone up a certain amount. Well, between 0 and 2 seconds, our average speed was 20 meters per second. So I've gone 20 meters per second. For 2 seconds, how far have I gone? Well, I've gone an average of 20 meters per second for 2 seconds. Well, 20 meters per second for 2 seconds would mean I've gone 40 meters. So now you're at a height of 40 meters. What's my average speed between 0 and 3 seconds? Well, let's say I started at 30, I ended up at 0. The average of 30 and 0, the halfway point, is 15 meters per second. If I've gone an average of 15 meters per second for 3 seconds, 50 meters per second times 3 seconds gives me 45 meters. So I'm now at a height of 45 meters. So our ball is going up and up and up, but it's going up by a shorter distance each time interval. So here it went up by 25, then it went up by 15, then it went up by 5. Let's see what happens now. So what's our average speed? Our average velocity between 0 and 4 seconds. Well, I've gone from a speed of 30 meters per second to negative 10 meters per second. On average, how fast am I moving if I've gone from 30 meters per second to negative 10? 30 plus negative 10 is 20. Taking the average of that, you just divide by 2, so that would be an average of 10 meters per second. If I've gone 10 meters per second for 4 seconds, I will end up at a height of 40 meters. Meters is up here. Try to be consistent there. So we're at a height of 40 meters. If I look where we are in that trajectory, we've gone up and up and up. We've hit a maximum at 45 meters. Now we're starting to head back down. So we're at 40 meters. What's our average speed between 0 and 5 seconds? Well, I've gone from plus 30 meters per second down to negative 20. 30 plus negative 20 is 10. Divided by 2, that's an average speed of going up by 5 meters per second. We do that, move at an average speed of 5 meters per second for 5 seconds. Therefore, 5 times 5 gets me a height of 25 meters off the ground. Now we can see something here. If I look, I can see this is symmetric about the 45. 45, 40, 40, 25, 25. If I kept going, I'd get 0, 0 after 6 seconds. So we'd be back at the height we started at. What this tells me is that the motion, a plot of the height as a function of time, should be symmetric. This will be the case for constant acceleration. Let's see what a plot of position versus time looks like. And since velocity is changing, we can also look at a plot of what velocity versus time looks like. So plot my position as a function of time. We'll do that first. I start off with a height 0 meters at 0 seconds. Let me just get some numbers in here. And so we go up to a height of 45. I'm just going to make this 50, 40, 30, 20, 10. Let's make a plot of my motion. Well, at 0 seconds, I'm up 0 meters off the ground. 1 second, I'm up 25 meters off the ground. That'd be about here. At 2 seconds, I'm up 40 meters off the ground. That'd be right here. At 3 seconds, 45 meters off the ground. At 4 seconds, I'm 40 meters off the ground again, symmetric. At 5 seconds, I'm 25 meters off the ground. Should be over here. Now you can see, we get a nice symmetric curve. It's kind of bowl-shaped, upside-down bowl-shaped. That curve has a nice name for it. This is just called the parabola. So the equation of motion, the equation for y as a function of t, should be the equation for a parabola. What about the velocity as a function of time? Well, we can do the same thing. We're just going to make a plot of velocity in meters per second as a function of time in seconds. Again, we're just going to put our 5 time units down here, 1 through 5. Again, we'll want to put some coordinates on our y-axis. We go from 30 to negative 20, so let's say it's 30, it's 20, it's 10, 0, negative 10, negative 20. Let's see what our graph looks like. Well, at 0 seconds, we're moving at a speed of 30 meters per second. At 1 second, we're moving at a speed of 20 meters per second. At 2 seconds, we're moving at a speed of 10 meters per second. At 3 seconds, we're moving at a speed of 0 meters per second. 4 seconds, we're moving at a speed of negative 10 meters per second. And at 5 seconds, we're moving at a speed of negative 20 meters per second. So this also makes a nice curve. In fact, there's not much of a curve to it at all, it's just a straight line. A couple of things to point out about this. We talked about our velocity. Really, this velocity has a name. It's our instantaneous velocity. Velocity itself is changing. However, right at 0 seconds, my velocity is 30 meters per second. Right at 2 seconds, my velocity is 10 meters per second. At that instant, I can look at and define the velocity. We've said before that the velocity just corresponds to the slope of a position versus time curve. Let's check and make sure that's the case. So we get a slope that changes over time. It goes from positive to negative. We can see my velocity also goes from positive numbers to negative numbers. Where does it cross over from positive to negative numbers? Well, here, I have a slope of 0. Here, we can see that at the time my slope is 0, I've got 0 velocity. 3 seconds, I have no velocity, and therefore no slope. The same thing, the same rules about slope being equal to velocity works even if velocity changes. The slope at any given time tells me the velocity at that time. Another way to put that is to say that the velocity versus time graph is equal to the slope of the y, the height versus time graph. Say that again. The velocity versus time graph is the same. It's identical to the slope of the position versus time graph. So we can say that the velocity as a function of time is the same as the slope of the position as a function of time curve. Velocity as a function of time is the slope of the position as a function of time curve. For those of you that have had calculus, you might say that the velocity is the derivative of the position as a function of time. Now, it turns out there's a way to go the other way. So there's a way to find not just the velocity from the position, we could also find the change in position from the velocity. So if I look here, I've got a triangle in that region. That triangle has a certain area underneath it. Area is just 1/2 the base times the height. Well, here my height is 30 meters per second. My base is 3 seconds. So that's 30 meters per second, which is the height, times the base, which is 3 seconds. 30 meters per second times 3 seconds is just 90 meters, but the area is 1/2 that. So the area under the curve up till 3 seconds is going to be half of 90, which is 45 meters per second. The seconds cancel. I'll get units of meters. So the area under this curve up to 3 seconds is 45 meters. Let's go over here. What height am I at 3 seconds? At a height of 45 meters. So it turns out that we can go the other way. We can say that the change in the position is equal to the area under the velocity as a function of time graph. The change in the position, my displacement, is equal to the area under the graph. Well, there's another word for this. Again, if you've taken calculus, you will know that the area under the curve is also known as the integral. So to go from velocity to displacement or position, you would take an integral. To go from position to velocity, you would take a derivative. Or equivalently, for those of you who have not had calculus, to get the velocity from the position versus time curve, you just take the slope. To get the displacement from the velocity versus time curve, you look at the area under the curve. What about the acceleration? What can I tell about the acceleration from these graphs? Well, we know that velocity is the slope of the position versus time curve. What about the slope of the velocity versus time curve? So what about this slope? Just by looking at it, I can tell it's negative because the slope goes down. And let's figure out how negative it is. Well, every second we go down by 10 meters per second. So we go down negative 10 meters per second every second. So that means my slope is negative 10 meters per second, or equivalently negative 10 meters per second squared. What else is negative 10 meters per second squared? My acceleration of gravity. So the slope of a velocity versus time curve is the acceleration. I can say acceleration is the slope of the velocity versus time graph. Again, if you've had calculus, we could say that the acceleration is just the derivative of the velocity. How can I get the acceleration from the position versus time curve? I'm not going to spend too much time going over how to do this. But the acceleration of a position versus time curve is known as the curvature. So if I had a straight line, there would be no curvature, and therefore no acceleration. So for constant velocity motion, we get a curve that has a constant slope, a position versus time curve that has a constant slope. So we have no acceleration. However, here we do have acceleration, so there's some curvature. Now, if my curvature is positive, I would have a positive acceleration. My curvature is negative, I would have a negative acceleration. There are technical terms for positive and negative curvature. I believe the mathematical terms are smiley face, frowny face. So here, we have a frowny smile, or a frowny face, which means we have a negative curvature, and therefore a negative acceleration, which is correct because our acceleration is negative 10 meters per second squared. If we had a positive acceleration, you would see a curve that looked like this. It would be a parabola that looked more like a smiley face. So the shape of the curvature, whether it's a smiley face or a frowny face, tells us whether the acceleration is positive or negative. The shape of the curvature on a position versus time curve. And the slope of a velocity versus time curve, whether it's pointing up or down, up tells me it's a positive acceleration, sloping down tells me it's a negative acceleration. Graphs and motion diagrams are a great way to visualize different types of motion. However, sometimes we'd like a more mathematical, more precise way to describe that motion. And for that reason, we have a set of kinematic equations. Now, we showed before that when we have a plot of position versus time with constant acceleration, we might get some curvature to that. We get either smiley face or frowny face, depending on the type of acceleration. So the smiley face and frowny face can be described mathematically by a parabola. And it turns out that our position is a function of time equation. Actually, I'm going to write this as x. Keep it a little more general. Our final position can be given using the equation of a parabola. It will be equal to the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. This is for a motion with constant acceleration. So my position as a function of time can be given by my final position, which is equal to my initial position, plus velocity times time, initial velocity times time, plus 1/2 the acceleration times time squared. Now let's look at our velocity versus time curve. Well, in the example we just did, we had a slope that went down like this. We could have a slope that goes up instead. It's just a matter of figuring out what our acceleration is. However, it will, for constant acceleration, just be some sort of straight line, possibly with a slope. It's the equation, if it's a straight line, then I should have the equation for a straight line, which in general is of the form y equals mx plus b. Here, the b, the constant, the intercept, is just your initial velocity, plus the slope times time, plus mx. The slope in this case, the slope of a position versus, of a velocity versus time curve, is the acceleration. So it'll be plus the acceleration times time. Now these two equations are great because I can solve for my velocity as a function of time, or my position as a function of time. However, sometimes you get into trouble because you have to solve a problem where you're not given the time. So we could do lots of algebra to solve one of these equations for the time, but that can be a little nasty. So what a lot of physics books do is they will give you a third equation that's really just a rearrangement of these two equations. Essentially what you do is you solve for the time in one equation and then you substitute it into the other equation. When you do that, you will get a third equation, which looks like this. d final squared minus v initial squared equals 2 times the acceleration times delta x, which is just x final minus x initial. These three equations are our kinematic equations. So for the motion problems we'll be dealing with, most of which will involve constant acceleration, we can use these problems. We can use these three equations to solve any problem. any problem involving constant acceleration. To show that I'm not lying to you, and that these equations actually work, why don't we go back and see if we'll get the same results in our chart from the problem we did earlier. So to remind you, we had a ball that we threw up at 30 meters per second. We assumed that the acceleration was negative 10 meters per second squared. Let's see if we can make the same chart just by plugging into these two equations. So what you're going to do is you're going to find the y height. It says x here, but that doesn't matter. The x is what we use for horizontal motion, the y is what we use for vertical motion. But the equation is exactly the same either way, whether I write it as an x or a y. So you want to find the height of the ball, which starts off at 0 meters. So your initial height would be 0 meters. Your initial velocity, we said that was 30 meters per second. The acceleration, we said, was negative 10 meters per second squared. See if when you plug in here, you get the same numbers that we got before for your y column. Similarly, let's see if we can get the same values for our v column. Again, our initial velocity was positive 30 meters per second. Our initial acceleration was negative 10 meters per second squared. See if when you plug in these numbers, and then plug in the different time values that you have over here, see and just check and make sure that you get the same velocity values that we found when we made our chart by hand.